Why? Why not absolute values? Any thoughts on that? Think about, well, what if I have to differentiate these? How do I differentiate when I have a absolute value? What's the problem? Discontinuous, right? Zero. But this is continuous. It's squared. Big two out stuff there. So always continuous. That's usually one. That's the right. And we've all taken basic statistics to assume that a regression, fitting a line to data. Use a norm for that. What norm? What are you trying to minimize when you fit a line to data? Use a regression.
The error.
It's the error. Not miss the error, but what? Squared error. Again, it's because I can differentiate it. Right? Squaring has another property as far as error is concerned. It weights what? Big errors more than small errors. This weights them all the same. And in the whole field of statistics where you have to use absolute values, you can do regression with absolute values, proper and stuff. You can do it. Right? Can it go to higher values? The answer, of course, is yes. Right? There's one called infinity norm. It's basically max value. So I have some vector here. The infinity norm of this is whatever the biggest value of x I have plus, plus and minus doesn't matter, but I'm also going to make the positive value when I return it. Why would I care about that? Infinity norm. Well, think about it in terms of error. Infinity norm for the error is what? The worst possible case I could ever have. And I might want to design to the worst possible case. The very last of this class, we're going to talk about linear quadratic regulators and things, which are basically using this idea. There's a whole other field here called H infinity controllers. This idea of what's like the worst possible case. Okay. All right. So, whole file. Now, the nice thing in MATLAB, it'll calculate all these norms for you. So if you say norm, you put in the vector, and then you say what one I want. 1, 2, infinity, things. So tell you whatever norm for that vector. All right, questions on norms? Okay. Orthogonality. Another thing you can know. Normal means the 2 norm is 1. The log of 1. That means the length of the vector is 1. Okay. So it implies important implication here. I have this matrix here, x vectors. The inverse of it is actually equal to the transpose. It's pretty handy for us. We don't need to worry about finding an inverse. I can just take transpose there if I know it's normal. What's ortho mean? Would be good. Perpendicular. Now, mathematically it means, whereas vectors go, means what? Dot product is 0. So you take one vector, dot product times the next vector, then we equal to 0. Because dot product of 2 orthogonal vectors is 0 because I'm looking at the projection of one vector on the other one. Perpendicular, 0 projection. Right? All right. So, are eigenvectors orthonormal? I can normalize them. I make it all the way to 0. Are they ortho?
Yes.
Yeah. They're orthonormal. Basically, this applies the number of independent vectors that I have. If any vector dot product with some other vector is not zero, it means they're not independent. Eigenvectors are all about that. Questions on that? We've seen everything before. All right. Questions on kind of linear algebra in general. We're not going to do really anything more in this class. I mean, we can do singular value composition, things like that. We're not much in this class. All right. Okay, let's. Let's start off with that. I have nice first order differential equation, homogeneous differential equation. How do I solve for x? What's the assumed form of the solution? What's that?
E to the minus.
Magnitude e to the minus at. Right? Right? So, we're going to run and solve for this guy. That's the whole solution. Like this. That's what we were under aiming for. So if this has this solution, e to the minus at, minus a, what would that?
The same.
Same. Matrix in that exponent. How do I get that? Matrix up there. Any idea? Let's say our matrix is have some random numbers here. What would be that? What's your first impulse to say what it is? first impulses, second impulse, what would it be? And third impulse, first impulse, I want to enter action is very simple as acting values. Most people think it's going to do this. Right? Most people think it will be that. That's how it is. A little more complex. Think about what these things do. Once I have my homogeneous solution here, what can I use that for? Say I know my initial value of x. That's not know what it is. How can I tell me what the value of x is in 2 seconds? Any thoughts on how to do that?
You plug in for time 0 and have your answer.
Well, time t equals 0, what is the answer? Huh? I can do this. You've ever done that? What these exponentials are telling you. That I know initial value, multiply the x, value sometimes whatever the values are, it's fine. I can do it for any time at all. I can actually do it for some here at 4 here. All I have to be able to eat minus 8 meters. Right, so I've got a solution to the homogeneous equation here. It's valid for all time. Okay. Can I do the same thing here? The answer is you betcha. Trick is how do I solve for that? E to the AT. Right? So let's go through what that means and how to find it. Has to be what we call a state transition matrix. When you think about that, the name implies what's going on. Right? Transition states from one time to the following time. Really solving the homogeneous equation. And the state transition matrix is the solution to the homogeneous equation. Homogeneous solution. Alright, so we did this for first word. Now I have to put it in minus a here to make it simpler. So homogeneous solution as u goes to 0. And what time all the work when we did this, it's series. We talked about series. Did you know you can solve any differential equation by a series? Did we ever talk about that in your differential equations class? In fact, the exponential is really what? The series that solves this problem. But I want to bring this up because this is the way to get one of the ways to get the state transition matrix. But I can always say that some value of x is going to be this whole series times the initial value of x. And you can go through to solve this sort of thing that x dot, that, put that into the homogeneous equation, and solve for all the C1, C2s, and so forth. And you'll get this form, this series. Did this in my math class one word, where it's 1, a times t, 1/2 a squared, t squared, so forth, over impact columns, and so forth. Well, that series happens to be the exponential. E to the at. Right? We just kind of skip ahead and do that. So I could define this solution, all this solution, this thing, called S of t, is simply e to the at. All right, think of this as a first order differential equation. This is a 1-by-1 matrix. All right? So we have it. Well, what do we know about the characteristics of e to the at? Well, I have to know if I shift in time. That's e to the at minus e to the alpha t. So I'm just shifting time. All right, shifted right off this edge here. That's e to the sp minus e to the minus tau. So I shift in time, I simply multiply the two. For negative ones, well, it's e to the minus at. Well, that's 1 over e to the at, or the inverse of s. It's all about 1 by 1, so it's pretty simple to see. And if I take it as some scalar, s to the nt, well, that's e to the nat, well, that's taking my solution s to the t to the nth power. Makes sense for 1 by 1, so e to the at. Right. Now let's deal with matrices. So here's our state equations. We worked the last 2 weeks gaining what A and B are here. Now we know what A and B are, let's look at. Let's look at an homogeneous equation. Basically, x dot is equal to a times x. Solution is just as simple as the first order case. I could take a series to it. Well, instead of scalars here, I have to do matrices, so I have a identity matrix, which is 1. C1 matrix, C2 matrix, C to the nth matrix, and so forth. Solve all of this. Substitute into the differential equation, get x dot also. All right, so here's x dot, x 0 times x times, or a times, same thing, solve for all the c's, and you get this form. It looks very similar to the original one, and matrix, a matrix, 1/2 a times a, one finally general form 1 over n factorial times a to the nth power. Same structure as the first order expression. So my solution matrix here, S of t, identity matrix plus total sum of these guys. Okay. That's called, say, transition matrix, and it is e to the at. All right. But if you look at what that's going to be, it's kind of messy. Quite what you have to do with the series. Okay. I'd like to be able to maybe find some other ways of doing this thing. So, x at some time t will be this s of t at that time times the initial condition, or s of t times the initial condition. Anything within the first order case. Properties of it. Same as before. Since they're all exponentials here, s of t plus tau is s of t times s of tau. Negative inverse of that. Take it to the power, s of t to the power, or multiply times n times t, s to the power n. Derivative, okay? This is going to be, well, it's e to the at, which is a e to the at, same as its standard exponential for first order. So this is the same properties we have for a scalar. It happens to be matrices here. All right. Makes sense? I'm going to get force response. What are we solving for here?